In this tutorial we are going to create a foil. We are going to create the board, and we are going to create the submerged part. We are going to start by creating a foil subfolder in our library. This is also where we are going to store our foil boards. To create our foil board, we are not going to bother too much. We are going to start from a Simons, Mini Simons type board, which already has its hydrodynamic scan, and which will therefore allow us to use this hydrodynamic scan to do our foil tests without having to do a scan. This tutorial assumes that you have followed the previous tutorials on dynamics, plank creation, etc. This is a fairly advanced tutorial. I will not repeat the basic concepts that have already been seen in previous tutorials. Here, I'm dragging a Mini Simons into my project so you can see the camembert. It therefore has its hydrodynamic scan present. So, in this Mini Simons, we are going to change some things to transform it into a foil board. We are going to start in the Mini Simons project to create a copy that we are therefore going to use. So to not distort the initial database of the software, when we use a model and want to transform it, it will be protected, so you have to save it as. So here I'm going to save as well, in my foil board folder, and I've called it Mini Simons foil board. Save. I am asked if the hydroscan should be saved with, since it exists, and of course, yes, I will keep it. This will allow me to speed up the testing phase. So now our project is board, Mini Simons foil board, which is, for information stored in my foil boards folder. I come back to my project here on the left, and I see my foil board here. The first thing I'm going to do is check its volume a bit. So as a reminder, even if it has a hydrodynamic scan, in fact, the board can be modified in certain dimensions. So you can still modify the board without destroying its scan. It allows you to create lots of families of boards without necessarily having to recalculate its performance basic hydrodynamics. So here in the size config, we will be able to put a little more thickness. 41 liters, and I want to go to 50 liters for this project. So I put 50 here. So the board will swell a little, and I will therefore have a board that is a little thicker, more buoyant, more volume as a base for my foil board. Here I'm going to remove the fins, so delete this one, delete this one. Here, I'm going to quickly create a fin that will serve as foil mast. So here I am going to add a fin like this to the project. It will be an opportunity to show how to create a foil mast. So here I'm going to add a standard static. So actually I didn't do a foil mast. I want to start from scratch. We will see how we make the mast from a standard static fin. So we take a static fin. We're going to edit it. So at this point, it's a fin, and we're going to create a fin shape. That's just a rectangle. Regardless of the scale, we want a structure that's a fairly elongated rectangle. We are going to soften the trailing edge here. We are going to do something a little straighter here. We would have to be more precise. But hey, for what interests me here, that's enough for me. And so I say that this is the shape of my fin, which is going to be my mast. It is a bit wide. But hey, it doesn't matter, I leave it like that. So I do apply and close, so it's a symmetrical nacelle, so it works both ways same. And I apply it to my project. At this point, There, I have a small piece of fin like that which does not look like much. But I will modify its size, and put a height of 700. Here I go to 700. So in fact, when we modify the height, we also see that we are modifying the width because it is a constant scale. And we see that it is the whole of our mast which has also thickened. So there you go, let's say it's a little wide. But I kept it like that. I'm going to place it so it's really a quick tutorial. We're not going to dwell too much on the exact shape. I'm placing it about here, 400 from the tail. So here, at this point, I made the foil mast. I'm going to save it. I'm going to select here. And save single static as. So I won't need to do it again. And I'm going to call it mast foil like this. I show also how to save mast. And I find it in my library. Here, at the level of the static fins, it is considered that the mast is a fin. I'll just have to slide it into a next foil project. So I have my foil mast. And here now I just have to add my flying structure. And I create a new foil. At this stage, we therefore loaded a new foil, and the default profile for this new foil is NACA 0006. So as a reminder, here, at the bottom left, we can see the foil identifier which reminds us of what it is made of. So W900300 mm, that's the span of the main wing, and the stabilizer. At 1116/186 square centimeter, this is the span of the front wing and the stabilizer. 0p/-5, it is the pitch of the front wing and stabilizer. And F0006, it's the shapes of foil. So front and back, so we can see that we have a 0006. It's a symmetrical profile which isn't necessarily the one we want to generate the maximum lift. It is better to use profiles with a certain camber. So we will immediately look in the foil in the static edition of the fin of the wing. We will immediately modify this profile. So I go back in the outline and fin profile modification interface. It's the same as for the foil. The foil uses the same interface, and here we will modify the profile. So here we see that the profile of the main wing is a 0006. We will want to put a cambered profile, and we will select here the NACA 2412 in cambered profiles. So we remember the NACA denominations. The meaning, for example, a NACA 2412. It means that it is a profile that has a camber of 2/10 of the chord located with a maximum deflection at 4/10 of the chord with a thickness of 12100 of the chord. So I select the NACA 2412. So here, be careful, little trick, I only selected from the list. It is still not applied to my wing profile. I will have to do, apply profile to all elements. And there I can clearly see inside my outline, the drawing of the profiles which has been modified. I will apply it to my project and close. And pay attention to a very important thing when applying a cambered profile. It is to check if the camber is in the right direction. That's very important. And there, in this case, we would not be in the right direction. That is to say that the extrados, the most curved part, must be on top. This is the part that creates lift, and if I look here, I can see that the upper surface is more cambered at the bottom than at the top. I can also go into the foil in this view to see the bottom profile a bit, and you can clearly see that the extradose is down. So I applied to the extradose, which is not in the right direction. I'm going to go back to the editor, and I'm going to reverse the extradose here on the right. I go to the other side, and I don't forget to apply it here. And so there I see that my extradose has been passed over the top. I apply globally, apply and close, and so here I check and I see that my extradose has passed over it. There I have a shape with an extradose on it. So there you go, I changed the profile of my foil. Now, I'm going to check if the dimensions of this foil are in line with my project. So my project is to fly an 80 kilo guy, with this foil, in a wave of about 1 meter. So there are travel speeds between 12 and 15 kilometers per hour. So I'm going to go to the foil tool and check if I can fly it. So when I go to the foil tool, I have to switch to the dynamic option. So I have a request that is made. I click yes, there I switched to dynamic mode, and I'm going to go to the foil tool. Open the foils tool and adjust its parameters so that it makes my guy fly at the desired speed. So the first thing I'm going to do is select the speed I want here. For my foil, I'm going to put it at around 14 kilometers per hour, rather 15. I say that my foil must fly with an 80 kilo guy. At 15 kilometers h 15.1, 4.2 meters second that I've set here. So I'm going to use the autospan adjustment function for the condition named above. So I'm going to click on balanced wingspan with weight. And so there, the software will detect the best angle for this type of foil profile and adjust the width of the foil so that it flies my 80 kilos. 82.73 kilos because there is the board that is counted with. So at this stage, I have a wingspan that allows me to fly at this speed, and this weight there. I'm going to move all that forward. Not too far back either. I can have fun repositioning the surfer to see where he will be exactly. That's roughly here. And so in these flight conditions, I see that I have a glide ratio of 22.1. So the glide ratio of a foil is the lift divided by the drag. So 22.1 means that in fact it carries 22 times more than it drags. It's his performance, let's say. I'm going to adjust that here. Because when we do a surfer replacement, sometimes we have not exactly the right balance here. So I like to do a calculation before moving on to something else. There, I estimate that in this state there, I have a foil, which corresponds to my project to fly an 80 kilo guy on this wingspan, with a wave of about 1 meter 50. At this stage, I'm going to record my foil, so I'm going to do record. That's it. And now I'm going to test my foil in the wave. We notice that when passing through the wave room, the dynamics automatically turn off. This is to avoid loading complications. Here is a wave loading. It still takes about 10 seconds if it has never been loaded. In fact, the board dynamics option goes off when you go from the shape room to the wave room, and you have to recreate the wave. You have a deactivation of the dynamics, so put it back to on. And then, we see our foil board which is in situation. So what we can say at this stage is that, if I display the dashboard, the speedometers, we see that we have 9.6 kilometers per hour, and our foil is already starting to fly. So we see in the dashboard, the different elements that may interest us to analyze the situation. So here we have the vertical and horizontal projections. We see in the projections, therefore vertical, that the vertical force of the fins, that is to say of the foil, is equal to the weight of the board and the surfer. We see in the horizontal projections that we have a component horizontal generated by the fins, i.e., a generated propulsion, whose totality is noted here 164 Newton. We have 16 kilos of thrust. We will see here that we can modify our trajectory by modifying our roll angle. So we will display the trajectory here in show curvature trajectory. And therefore there we will simply see what happens when we are in the process at that level. So we have an initial speed of 13 kilometers per hour. There we see that we are constantly accelerating. You can change the roll angle. Here, we will start a little straighter to gain time. You can also check the direction of the trajectory. If we have an upward trajectory or if we have a downward trajectory. If we are on an upward trajectory, that means the wave is catching up with us. And if we go faster than the wave, we will go down in the wave, and there, we will go on a downward trajectory. It's a small piece of information that tells us if we are being caught up by the wave or if we are ahead of it way down. It means that we are going down the wave. Here, I put myself a little bit of roll angle, to keep a trajectory parallel to the wave. And now, I will be able to analyze the capacities of my foil in this wave. We will be able to display. So I stop the wave. Well, going to stop at this phase from my foiling. To display forces data. Here, we will see the tab. So at the level of the display of the forces, we will therefore enabled the fins of which our foil is part. We will be able to see and display the lift. So we see here the lift of our foil parts. Here, when we pass over it, it gives us the exact force of this part there. Here, on this part of the fin which constitutes the right wing of the foil, we have 536 newtons, so 53 kilos, approximately, of lift. In this lift there we will display the horizontal component. And there we see that here, the horizontal projection of this lift there has a horizontal component, which goes forward. It is our propulsion. This is what makes our surfer accelerate when foiling. We also see that the rear stabilizer works upside down. It has a tendency to generate negative lift, to make us raise the foil. Let us say to tip it over the rear, and it has a braking component, a balance of forces which is rather negative. It slows down a bit, but the global component is here, and that is the resultant of our global foil. So here we have a bit of an analysis of our forces produced by the foil. We will also have an interesting element among these forces. It is the deflection force. What makes our foil turn is the lateral deflection generated by the projection of lift as a function of roll angle. Here, I'm almost zero roll angle. I restart the wave very slowly. But I see that if I'm going to put a significant roll angle like that, and there, I will stop the wave. We see that we have a lateral component, perpendicular to our displacement. Here, so I erased everything. I'm just going to show a deflection component. So I'm going to stop following the board. and reposition myself to better see the forces. There. And there, I just display the deviation. We have a deviation, which is generated by the projection of the lift. So I'm showing the lift here. The lift project horizontal and perpendicular to the trajectory. I see here this arrow down here called horizontal deviation, the force which is a projection of lift to the right, and which tends to bend our trajectory. This is what makes our foil turn along this trajectory. Here in dotted line. So if I modify my roll, what do? I therefore modify this deflection force. The more roll I have, the greater this deflection force will be. The more I will bend my trajectory, the lower the radius of curvature will be. The less roll I have, the less trajectory deviation I have, and the less I turn. So here I stop again. I see that with this roll, the trajectory deviations for each of the elements of my foil are given here. We see here that the front wing creates a deviation in trajectory which will be rather closing, i.e. we will close the radius of curvature here in roll to the left. So I will try to show it well. So my trajectory winds up and I turn to the left. On the other hand, if I look at the deflection of my rear stabilizer, it is the opposite. Rather, it tends to drag the rear. So we see that the stabilizer, depending on its pitch angle and its work, will rather tend to rotate or straighten or yaw our foil. So those are small settings that we will be able to adjust. And that will be the mastery of the master shaper, creator of foil. And it will be through these analyzers of forces that he will be able to balance and give character to his foil at will. It can therefore go really very far in analysis, and that is the business of the foil manufacturer and the shaper. So we see here that this tool allows you to see the forces, to analyze them and to balance them according to your wishes. We still have one little thing that we are going to show. It's in the history. We will show the story at the fin and foil. So the story of fin is in fact that we are going to record the performance of the foil. As the trajectory progresses, I relaunch and I move forward, and there I am going to select record data. And I record all the real-time force data from our foil. Here, I'm with a slightly interior roll. I rolled a bit outside to turn, to try to follow the wave as it breaking. And at the same time I record this data. We could analyze each element. So here in the history that was recorded. That's it, we've finished this short presentation tour of the foil tool, which allows the creation of foil for a given project.